Okay, so last time we stopped at the Slutsky's theorems. So just a quick recap of the end of our last lecture. We talked about three important results regarding the convergence in law. So we gave you three theorems for Slutsky. The first one is called the continuous mapping theorem. So in short, it's about given we have this convergence in law from x to n to x, and we have a function f such that the limit is in the continuity set of f with probability 1. So in other words, for all the values we care about, the function f is continuous at. So given those two, we can say after the transformation, we still have convergence in law. This is a very important result because it allows us to go from central limit theorem to a lot of other things. And we'll see this later. The second theorem is regarding using a surrogate convergence in law to derive our target sequence convergence in law. So let's say the surrogate sequence is xn converges in law to x, and our target sequence yn and xn, their differences goes down to 0 in probability. And as I said, this can be replaced by in law because the limit is just a constant. So given those two, we can say yn converges in law to x. This is what we want. This is what we start with. Again, this provides a way to use the central limit theorem, right? Because we may have xn as the xn bar, the sample average, but this yn may be some little modification on that term, but their differences are negligible. Therefore, we can derive the convergence for yn in law. The third statement, remember, we apply this as a proof, right? What this statement says is that we have two sequences, xn converges in law to x, yn converges in law to a constant c. Then if we couple those two sequences, xn, yn, this joint sequence will converge in law to the coupled limit. Okay, last time we said this c cannot be replaced by a random variable y. And we give you a counterexample, but it may not be that obvious. So I will give you a better counterexample for now. But before saying that, I want to say, just remind everyone why we use B as a proof to prove C. So in other words, what we have is basically using a surrogate, right? So what we're saying is that we have xn, so proof based on B. So in that proof, our surrogate is xn and c converge in law to xc. This is from the condition immediately. And we have x and c, the surrogate, minus our target sequence, x and yn. This will converge in probability to 0. The reason is that yn converges in law to c can be replaced by p, convergence in probability. So that will give us this. So together with statement B or theorem B, we can have x and yn converge in law to xc. That's it. Okay, and regarding the counterexample, let me just give you maybe an easier one. Counterexample of C. So for this, let's imagine that we have two independent sequences, okay? x1, x2, and so on, y1, y2, and so on. So these two sequences are independent, and they are each IID. So in this case, or maybe we can say each IID with mean 0 variance 1. I'm just making the scenario easy. Y, 0. Okay, given the simple scenario, then by the central limit theorem, right, we would have convergent law to standard normal and also Ym. Okay, so now let me just denote a random variable. I let a random variable z that follows the standard normal. Then by our definition of convergence law, we have root n x n bar convergent law to z. This is correct. Root n y n bar convergent law to z. This is also correct. But if I put it together, root n x n bar y n bar as a vector, two-dimensional vector, this does not converge in law to z and z. The reason is that on this side, on the left-hand side, we have independence between x n bar and y n bar. On the right-hand side, it's the same thing. So this is just an example to show that we cannot generalize this z to be a random variable. And I hope this clarifies the question I obtained after the last class. Okay, does it make sense to everyone? So in other words, convergence in law says nothing about the dependence, right? So this and this can be independent, this and this can be independent, like we said before. But for convergence in law, convergence almost surely, for those stronger types of convergence, we cannot have independence between the limit and the sequence. Okay, so that's Slutsky. And with the Slutsky theorem, we could have a corollary, which will be an application of or combination of A and C. This is very important. So this says that, let's say we have xn in d-dimensional, yn in k-dimensional. And again, for following the condition in C, xn converges in law to x, yn converges in law to c. So given this, let's say that I have a function f that maps from d plus k dimensions to any other dimension, okay? And we need to require that the limit, joint limit, x and c is in the continuity set of f with probability 1. So you can see this is basically the condition from A. This is the condition from C, from Slutsky statement C. Combining those two, we would have that the function f applied to, I'll just write it as this way, xn, ym, this joint vector will convert in law to f applied to the limit x and c. Okay, so this will be an application, or this corollary, we will use it to show the asymptotic normality of the t statistic. So that will be the important application. So in this example, we have, again, our usual setting, x1 to xn, IID, mean, mu, variance, sigma square finite. Okay, given this setting, right, so, and the t statistic is defined based on the sample variance. So this is something we haven't seen often. Okay, the sample variance, we use the notation as n squared. It's defined as 1 over n or 1 over n minus 1. It doesn't matter that much here. N minus 1 is the unbiased version. But since we're talking about asymptotics, right? N minus 1 and n are asymptotic equivalent. So I'm writing 1 minus n here just for simplicity. Xi minus xn bar squared. Okay, that's our sample variance. Then what's the t statistic? The t statistic, I just use this t, is defined as what? It's defined as xn bar, or I should say, yeah, it is xn bar minus mu, okay, divided by Sm. That's what we have. And you remember that why does it involve mu here? And we know mu is actually unknown in applications in practices because this is a true parameter. Recall that in our application of t statistics for doing a t-test, our null hypothesis will specify the value of mu. It's usually mu equals 0. So that's why in that case, you are just putting in the mu from the null hypothesis. So you don't have any unknown parameters here. But here we're just talking about this t-statistic in general. So we have this formula. Okay, and think about how different this is compared to the, what's that? Compared to the central limit theorem we talk about. Okay, by central limit theorem, what we have is root n xn bar minus mu. Okay, converges in law to normal distribution with mean 0, variance sigma squared. So just write it another way, we have root n xn bar minus mu divided by sigma converges in law to standard normal distribution. Okay, so comparing the t statistic, and actually I think I missed one thing in the t statistic, sorry, I need to have this divided by root n here, right? The sample standard deviation, which is the square root of the sample variance, that's the Sm. That's only for one xi. Here I'm talking about the average, so I should scale this, divide this by root n. So in other words, you see that what's different between the t statistic and what we have from the CLT is here. We have Sn in t statistic, but from CLT, we have sigma. Okay. However, you know, we do have something we can apply or talk about for the sample variance. Okay, so note that the sample variance can be written in another way. I'm leaving this to derive for yourself. Can be written as the average of xi squared minus the square of xn bar. So this is very similar to the variance can be equal to the expectation of xi squared minus the square of expectation xi. It's very similar. Okay, so given this, you see, by the law of large numbers, right? And also, we have the Slutsky to help us. So you can think about by, let me just put it here, by the law of large numbers, what we would have is 1 over n, this average and xn bar. These two things will converge in law probability or almost surely. They all hold to what? To the expectation of each, okay? So the expectation for the average of xi squared is actually the expectation of xi squared. And we know that's mu squared plus sigma squared. And this is mu. Okay, so given this, then we apply Slutsky on statement A to transform to have a function that maps this to the Sn squared. And we can do that. And we can show that the limit still converges the same function applies to the limit. So Slutsky A, okay, we can have Sn squared converges in law. So I'm sticking with law because we have law over there. So this will converge to the transformation of this, which is basically this minus the square of this, which we have sigma squared. Okay. So I can take a square root on each side because square root is also continuous, right? So I can have Sn converges in law to sigma. Okay, so given all this, what can I do? I'm going to apply this corollary. This corollary is actually you can also say this one is an application of the corollary. You can also say that as well. But what I will have from the corollary is that given this convergence of Sn to sigma, and given this result from CLT, combining those two, I would have, I'll just write it here. So root m xn bar minus mu divided by Sn instead of sigma would convergent law to standard normal. Okay, so the reason is because that sigma over here is a constant. So that's why we can apply this result, that corollary result. So what does this imply to us? It says that our t statistic asymptotically follows this standard normal distribution. And this is not something we use that much in t-test. The reason is that in t-test, right, under the assumption that x1 to xn are IID Gaussian or normal, we can have an exact distribution for the t statistic. Okay, so let me just write it down. When x1 to xm are IID normal, okay, we would have this t statistics follows exactly t distribution with n-1 degrees of freedom. This is a distribution our founders of statistics define, or the student t. I think that's the pseudonym for the person who invented the t distribution, who derived the t distribution. But this is an exact distribution under this Gaussian assumption, and it has nothing to do with how large n is. Even though n is very small, say 3, we still have this as an exact result. But what we derived here previously is an asymptotic result. It's about when n goes to infinity, what happens. So comparing those two, what implies is that the t distribution, okay, this distribution would converge, or maybe I should make it more explicit. So I say t follows this. Let me denote another random variable follows standard normal. Okay, so what combining those two results, what tells us is that this t distribution would converge in law to standard normal as n goes to infinity. Okay, maybe to help you understand this better, I should carry n here in the t statistic so you know sample size is here. So in other words, t distribution, okay, when the degrees of freedom goes up to infinity, the t distribution will converge to standard normal distribution. And this is a fact. And also we know that if you have t very small, then comparing the t distribution with standard normal, the t distribution will have heavier tails. In other words, it's less concentrated on 0. But as you increase the degrees of freedom, you will converge to standard normal. Okay, so does that make sense? And so in our asymptotics, we don't use t distribution because in this distribution, the sample size is finite. All right, that's an application of Slutsky. So I said here, our Slutsky discussion is for the convergence in law, but we can change the distribution, change the convergence to other modes. So for example, we can have everything changed to be probability. Okay, so erase everything. Just leave the statements So if we have this as convergence and probability, this will be convergence and probability for statement A. For statement B, convergence and probability, probability. And for statement C, when we change it to convergence and probability, then this limit can be random. And that's the nice dependency we would have from convergence and probability. We know that if the convergence and probability, then as n goes up, this yn and y will be close to each other in most of the realizations. So we have that coupling and coupling here. So that will make sure we can also have convergence and probability for the joint distribution. Okay, and this is also should be something we can prove based on the definition of convergence and probability. And again, I would say that if you have this already, you can move down to here, use B to prove C. So that's the convergence and probability version of Slutsky. And furthermore, we can replace P by almost surely, and still everything holds. But I don't think we use that often in practices. So convergence and probability is most often used. But I'm just making it here. So if this is almost surely, this is okay. So that's all about Slutsky. So you can think about it as a very useful tool for us to go from what convergence we have to what we want to prove or want to derive. So it gives us very useful techniques that we can use. So in addition to Slutsky, I want to say, okay, the Slutsky is a very, it's basically based on very accurate transformations, right? So next thing is also very widely used, but that one would be based on Taylor expansion. In other words, the next thing we'll talk about depends on a large M. So we need is basically an asymptotic result. While here, all the transformations here like this doesn't require M to be large, right? And these are just deterministic transformations. Or I should say, the next one is also deterministic. There's no randomness involved, but that the next one is more like an asymptotic approximation. Okay, so the next result, I think most of you might have learned this from other classes. It's called the delta method. It's commonly known as the delta method, but in our notes, we call it Cramer's theorem. It's about the same thing. Okay, so it's about the asymptotic distribution of a transformed random sequence. And the transformation has nice gradient and continuous in a neighborhood of the mean. So given that if you have the original sequence following convergent to some random variable in law, then we could apply the transformation in some way to the limit. So we can have the limit of the transformed sequence. That's the basic idea. Okay, so we have this xn. Okay, we have this xn in Rd. We talk about the vector form. And we have this function g maps from Rd to another possible dimension. And we will require, if you recall, this gradient, okay? So for the gradient, g dot, we would require it to be continuous. Or actually, just to remind you, what will be the dimension of the gradient? So if this k is equal to 1, we have the gradient as a row vector. But if this is a k, then we would have it as k by d. Okay, that's how we define the form for the gradient. So in other words, if a k equals 1, it's a row vector. And for the other dimensions of the value, we just go down. So we have a matrix of K by D. Okay, so what we require about this gradient is that we would need, so let's say that we already have some nice result about xn already here. So we have this nice result, for example, from the central limit theorem, xn minus mu convergent law to some x. I'm not specifying the x to be normal, just to be general, but you can think about this as the central limit theorem. So that's the form you are familiar with. And we care about this mu, right? It will be the center of our, or it will be something in the asymptotic distribution. So what we require for this G is that we need this G dot, the gradient is continuous in a neighborhood of mu. So in other words, we are not only requiring G to be differentiable, but its gradient, first order differentiation must be continuous around this mu. So given this, we can do some expansion, basically. That's why we need this. Okay, so with this, then the conclusion about this Cramer theorem is that if we apply G function to xn correspondingly to mu, then the asymptotic distribution would be, we still multiply the same root n, would be converging in law to the G dot gradient function evaluated at mu, right? So we call our dimension. This is K by D times X. And recall that X is RD. So we are going to converge to a vector that's k-dimensional in the k-dimensional space because gxn and g mu will be in RK. So in other words, you see, it's a very nice result. It shows that even though the G function may be nonlinear, but the limit is just a linear transformation of the original limit. So this is the delta method, and it has very nice properties because of this linear transformation in the limit. So just give you an example. In the special case that we are under the central limit theorem. So in that case, if we have, so let me just use the central limit theorem result because this is something we're familiar with. This is a D by D covariance matrix, okay? So given this central limit theorem result for such a G, what gives us root n g xn bar minus g mu converges in law to a linear transformation on this, right? And we know that how the linear transformation will enter the covariance matrix. We will actually multiply it for twice. First on the left, then on the right of its transpose, so that we can have, so it's similar to the univariate case when we scale a random variable, then the scale will be squared in its variance, similar to that. So this will be 0 g dot mu, this is a matrix, times k by d matrix times the sigma times g dot mu transpose. This is d by k. That's it. So in other words, when the limit is a zero mean Gaussian distribution, the delta method will still keep the transformed sequence asymptotic distribution as Gaussian. The Gaussian form stays. What's changed is only in the covariance matrix. And the covariance matrix will be scaled based on the gradient of the function at the asymptotic mean, at the mu. Okay, so this is the result, this is the form, and we will quickly prove it using the techniques we already have. Okay, so in other words, if you recall, we talk about the mean value theorem, which is very similar to the first order Taylor expansion, except that it's exact. Okay, so we will use that to expand our G around mu. That's what we will start with. And this is why we need this G dot, this gradient, to be continuous in the neighborhood of mu. Okay, so let's do it. Okay, so basically, let's say that given the condition, we assume that G is continuous in this neighborhood of mu. We'll just write it out. X in RD such that the distance between X and mu is less than delta for some delta positive. So here, this distance is just like the Euclidean distance in the RD, right? So we define a delta neighborhood of mu. So then, given the mean value theorem, we could expand G around mu, G mu. So we can write Gx equals G mu plus this integration. We have some value between 0 and 1, changes between 0 and 1. And we let the gradient to go from mu plus this value v times x minus mu. Okay, so this is just like an interpolation from mu to x dv. Integrate over those v. Okay, times x minus mu. Okay, so that's what we have from the mean value theorem. And now we are going to use we're going to get what we need from here. Okay, so you see I have Gx, G mu, right? So if I change my x to be my xn, I would just do here, and here. Okay, so I'm expanding Gxn in terms of G mu. So now I move G mu to the left-hand side and multiply root n. Okay, then you see, based on what I have above, it will be that integral. Just copy it down. G dot mu plus v times xn minus mu dv, okay, times root n should stay here, xn minus mu. So you see, I have the form I have in the condition, right? So the left-hand side over there is the thing I want to prove. The right-hand side involves my condition. Then I only need to deal with this part. Okay, and now because of this condition gave us a very important result. Actually, think about it. Okay, so first of all, because of this root n, right? So if you let this root n go to the other side and let the n go to infinity, then essentially this is going down. So because this x, we need to have some, although we didn't say it, but we are actually implying that this x has some, it's not really infinity. Okay, so given that we can say, let me think. If, so for the stronger condition, if we just want to say this x has finite second moment, okay, with that condition, if you divide this root n to this side and let n go to infinity, then you are going to have this right-hand side x divided by root n converge in quadratic mean to 0. And that will imply this right-hand side will converge in law to 0. So because quadratic mean convergence implies convergence in law. So what I want to say is that we would actually be able to say xn converges in law to mu based on that without the root n. This is something we imply from this convergence. Okay, and with this convergence in law, we know we can go stronger, right? So this can be convergence in probability to mu. So with those, we are able to handle this part. The reason is that this is an integration and v is going from 0 to 1. And now we have this part converges in probability to 0. Okay. So what can we say about this? When this term goes down to 0 in probability, what can we say about this integration? Any idea? Right, so if we have, so right now, the thing is that this term, this is a function, right? So we are basically having this argument, this whole argument, no matter what v is, let's pretend v to be fixed. We're having this whole argument going to improbability to mu. That's what we have, right? And then the question is, given that, can we say that this g dot mu integration for this v from 0 to 1, because basically v is gone. So then can we say that this whole term is convergent in probability to g dot mu? That's it. Once we have that, then we're done, right? So we have convergence in law for this multiplier, this part, and we have this part convergent in law to x. So together, you see, this will converge in law to x. So based on what we just see from that Slutsky theorem, we would have a nice result. That is root n gxn minus g mu would converge in law to this g dot mu times x. So that's the conclusion we have in the Cramer theorem or the delta method. Okay, so that's pretty much it. So, and also I have to say that here the continuity of the g dot, it plays a key role in the neighborhood of mu. Otherwise, we cannot do that. But usually, you see, when we apply the delta method, the function g we deal with are some very nice, easy functions. So usually, we don't need to worry about this continuity in our applications. Okay, so now we are going to do a quick application of this delta method to our central limit theorem. So let's come here and do, again, we are in the situation we are familiar with. So that is example 1. We have x1 to xn. they are IID, univariate, okay? And they have mean mu, variance, sigma square, finite. So that usual setting. So then by central limit theorem, we already know that root m xm bar minus mu converges in law to normal, zero, mean, variance, sigma square. We have this. Then the question is, what is the asymptotic distribution of xm bar square? The square of the sample mean. What is the distribution of that? So now, you see, this is an obvious application of the delta method, right? The g function is just a square function. So to answer this question, we just let g x be x squared. Here, x is just a notation for the argument to denote the function. Then when we take the derivative, first derivative, then g dot x is 2x. Okay, so we will apply the Cramer theorem, which means we're going to apply this version specific to the normal limit. Okay, so now we need g mu, right? That will be 2 mu, 2 times mu. So therefore, we would immediately have xm bar square minus g mu. So that will be mu square converges in law to normal 0. Because this is a univariate case, we will just have g dot mu square times variance. So that will be 4 mu square sigma square. That's it. Okay, we have this result, which seems to be nice. But we have to consider a special case when mu equals 0. So the issue arises when mu is 0, then the variance will, asymptotic variance will be 0. Right? Because 0 variance, 0 mean, that's a point mass at 0. But that is not meaningful to us, right? This just tells us, okay, this tells us nothing more than xm bar square converges in law to mu 0 at a rate faster than root n. At a rate faster than this root n. That's pretty much it. So multiplying root n to it will not counteract this convergence here. Or maybe I should say 1 over root n. Yeah, faster than that. So in other words, what we want to have actually, think about this distribution, is that we know by our, we can have the law of large numbers and then the continuous map together. We know already our xm bar square will converge to mu square as n goes to infinity. We know this, but we don't know. But the asymptotic distribution offers something beyond that. It tells us if we just multiplying this divergent constant, which goes up as n goes up, then it can counteract the shrinkage over here. So we can have a stable distribution, not related to n. That's what we have for central limit theorem and also in this result. But when mu is 0, then this root n is not enough to counteract the shrinkage. We still go down to 0. Then it suggests that we will need something bigger than root n. Okay, so that's the message we get immediately. So let's think about it. Okay, what can we do in this case? So an alternative to the delta method to solve this problem is to think about the Slutsky theorem, statement A, we just learned. So when mu is 0, okay, what we have from the condition is that root n times xn bar, mu can become convergence law to normal distribution. Okay, we have this. And so if we divide sigma to the left-hand side, we have root n divided by sigma times xn bar, convergence law to standard normal. Okay, now we are going to apply that Slutsky. Statement A, the continuous mapping theorem. If I square the left-hand side, I know I can square the right-hand side, right? The distribution. The reason that I can square the random variable that follows standard normal. And we know what that is. It should be chi-square 1 by definition. So that's just an application of Slutsky A because square function is a continuous function. So we have root n sigma x n bar. Okay. Square convergence law to chi-square 1 distribution. So basically what I did on the right-hand side is that for a random variable, standard normal random variable, if I square it, then its distribution will be chi-square 1. That's why I can write chi-square 1 here. So then what's the left-hand side? You see, just reorganize it. It's basically n divided by sigma square times xn bar square convergence law to chi-square 1. So this answers this question for the case when mu is 0. And clearly you can see what happens is that for this left-hand side, or if you want to have a form similar to what we have right here, I can just keep n here and I multiply sigma square to here. Okay, sigma square times the chi-square 1. And or I can write it another way to say that if I have a random variable z follows chi-square 1, then the limit, okay, this limit n times xn bar square would converge in law to sigma times z, okay, whose variance will be squared. The chi-square will be sigma squared. So it's basically equivalent to writing it that way. But the key thing here is that what I want to say, or actually, my bad, I should keep sigma squared. Yeah. This is correct. Sigma squared times z. So that's what I mean for chi-square. This is what I mean for sigma squared times chi-square 1. It's basically a chi-square random variable scaled by sigma squared. So you see, comparing this to we call this degenerate case. Degenerate means that the limit is no longer a distribution, but a point mass. Comparing those two, you see, by enlarging this divergent constant from root n to n, we are able to stabilize the distribution. So it no longer degenerates, but we have a stable distribution, scaled chi-square 1. Okay, so that's what I'm saying. This Slutsky statement A is also a way for us to derive the asymptotic distribution of a transform sequence, in addition to the delta method. The delta method uses the, linear expansion approximation so that we can still keep the distribution of the limit. If it's normal, after the transformation, it's still normal, but it doesn't always work because we may have a degenerate case for the variance. So in this case, the Slutsky, which doesn't do any approximation, would work and could be a solution. Okay, does that make sense to everyone? Okay, that's example 1. Let's see another example. Okay, the other example is the same setting, but we are looking at different transformation. So now the question is, what is the asymptotic distribution of 1 over xn bar, not xn bar squared? So another transformation, and we will use the same strategy, delta method. So now we let gx be 1 over x, okay? And we would have, similar to here, the derivative gx would be negative 1 over x squared. And for both cases, we have to exclude x equals 0, right? By the definition of the function. So, but when it's 0, we just have infinity in both cases, and we will actually need to deal with that. So then by the delta method, we just directly apply it without much thought. We will have, right, we transform this, then we transform mu, and we transform the variance. So this will give us negative 1 over mu squared, and we have to square that. So we would have sigma squared over mu fourth. Okay, that's the asymptotic distribution. And again, this only holds when mu is not 0. Okay, but even though we could have this result by adding the constraint that mu is not equal to 0, we have this, but we do need to, I want to make a point here is that even though based on this asymptotic distribution, if I ask you, what is the asymptotic mean of xn bar or 1 over xn bar? What's the asymptotic expectation or mean of 1 over xn bar? What's your answer? Given what we have from the delta method. Yep. 1 over mu, right? It should be 1 over mu. Yes, that's a correct answer. But if we have, since here we don't say anything about the distribution of x1 to xn, but if we do have this nice ideal case when x1 to xn are IID normal or Gaussian with mean mu variance sigma squared. In this case, if I ask you the question, what is the expectation of 1 over xn bar? And interestingly, the answer is that it doesn't exist. So it's infinity, basically. The reason for that is because, okay, so given those things, right, we can have xn bar itself is Gaussian, mean sigma squared over n. So we have that. So if you're interested, you could directly do this integration by just doing, this is just, okay, right? This is 1 over x, sorry. And then the density function, I'm just writing it down. Okay, so exponential. Okay. Okay, if we just do this integration by definition, we will be able to show that it doesn't converge. This is a divergent integral. The simple reason is because we do have x equal to 0, and around that region, we have a pretty large positive probability density. So that makes this doesn't converge. And so I actually updated my notes. If you're interested in checking this, I added a URL there, so you can check a detailed discussion about this issue. But basically, the exact expectation under this ideal Gaussian assumption for the data, for the random variables, is actually infinity. But nevertheless, as long as this mu is not 0, we do have an asymptotic expectation for this 1 over xn bar as 1 over mu. So this tells us that the asymptotic variance, or the asymptotic expectation, cannot be simply used as expectation. So these two are different concepts, and I'm just trying to emphasize that. I think this counterintuitive example is actually very interesting for motivating us to think, wow, it's possible that even though this thing exactly don't have an expectation, however, when we let the sample size go to infinity, then its asymptotic distribution does have a center. Yeah. Okay, so do we have questions for this example? Okay, so if not, then let's look at another example to see the application of the delta method. So previously, recall that in the T statistic example, right, we showed just a few minutes ago that Sn squared sample variance converges in law to, or probability to sigma squared. That's what we showed before. Now, the next question is, what's its asymptotic distribution? This only gives you a limit. It doesn't give you the asymptotic distribution. So obviously, we still need to subtract sigma squared to the left-hand side and multiply the difference by some divergent constant, probably root m, probably n. We'll see which one would work. So example 3 is the asymptotic distribution of sample variance. So this will be a very good exercise that will practice the things we learned before. Not just the delta method, but also the law of large numbers, etc. So again, just recall, we have Sn, we can write Sn squared as the difference of two sort of averages. One is the average of squares. One is the square of the average. Okay. So just to be consistent with our notes, we are going to denote this term just as, and let me see. Yep, we're going to define this as the mxx. What it means is that this is the mean, sample mean of square. So that's why we have 2x here. While we define this as xn bar as mx. Okay, so mx is just the mean of x1 to xn. mxx is the mean of x1 squared to xn squared. And so what we will do is that we are going to apply delta method to the asymptotic distribution of these things, mx and mxx. The reason is that we can actually derive the asymptotic distribution for this two-dimensional vector because both are averages. So we can apply central limit theorem. So we'll see. So by the central, so basically you can think about which is, I'm going to write it this way so it will be clearer to everyone. 1 over m summation xi squared. So I put my data into this two-dimensional vector and then I take average. So I will have this vector of averages. Okay, so then the central limit theorem by the CLT, what we would have, right, we should expect is that the root n of this average minus, it will be the expectation of this. Expectation of xi squared, right? It should converge in law to a two-dimensional normal distribution. This is a zero vector, which is 2 by 1, two-dimensional. And the covariance matrix would be what? It would actually be, I'll just write it as the covariance matrix of xi squared. And this will be a 2 by 2 covariance matrix. So for this matrix, I'm going to just do a little derivation. So first of all, for the mean, this part, it should be obvious, right? The first dimension is just mu. Second dimension is mu squared plus sigma squared. So the square of the mean plus the variance, that's what we have. And the more difficult one is about this covariance matrix part. We don't have independence between the two dimensions, obviously. So we would have, I'll just write it here. It's the variance of xi, the variance of xi squared. Okay, here it will be the covariance of xi squared. Here I would have the covariance of xi squared xi. That's it. Okay, but now I'm going to show you a strategy that is, given this laid out, we don't need to simplify this covariance matrix immediately, because ultimately we are going to, if you recall the delta method, we are going to left multiply this by that g dot mu and right multiply this by that g dot mu transpose. So it's possible that we will have some cancellation. So some terms may go away. So we don't have to keep everything, calculate everything for now. So in other words, I'm going to denote this by sigma. Okay. Now let's move to this left-hand side, or maybe just use this part. Okay, so now we think about what's the g function. So what is the g function that will give me? So the g function will be R2 to R1. So maps from 2 dimensions to 1 dimension. So I'll just write it as the g function of mx and xx. So that's the function I'm looking for. What g function can give me Sn squared from this vector mx and mxx? So clearly we will see g, let's say first dimension is x, second dimension is y. Then this g function should clearly be y minus 2x, right? Based on the relationship between Sn squared and mx and mx, mxx and mx over there. So therefore, now what's g dot? We said it's a row vector. First dimension is a partial derivative against x. We will get -2. Second is partial derivative against y. We will get 2y. Okay, that's the row vector we have. So now we are going to apply this g function to our mean. Here, right, the mean is this. So just applying the g function, we'll have g dot. That will give me mu, g first. G mu squared plus sigma squared. Clearly, by the definition, we would have, oops, my bad. Sorry, I think, oh, is it correct? Mx, okay, sorry. I think this is not right. It's actually y minus, sorry. I don't know why I'm writing this. Y minus x squared, sorry. Okay, so now, yeah, that's NYY minus MX squared, correct. So then we take the partial derivative, I will get negative 2x and 1. Okay, that's the correct version. So now applying this G to the mean vector, okay, I'm just going to replace this by mu squared plus sigma squared. So it's clearer to us. So applying G to that asymptotic mean, okay, we'll have this minus square of this. So we're left with sigma squared, which is consistent with what we have, right? As n squared converges to sigma squared. Now the gradient, G dot applied to the asymptotic mean, mu squared plus sigma squared. Now, again, this is x, right? So we have negative 2 mu. The second thing is just 1, always 1. Okay, so now this is something we have to left multiply that sigma, this 2 by 2 covariance matrix, and also this transpose will be multiplied to that. So let's see what it looks like. So this G dot mu square plus sigma square, left multiply sigma, right multiply the G dot mu square plus sigma square transpose. Okay, so then let's take a look. So we would actually be able to show that this is just equal to let me see, mu sigma square. Oh, there's one thing I need to, okay, sorry, I think I missed one important thing here. That is this mu. Okay, so the thing is that what we have here is, but actually it will not affect the result. It's just make things a little simpler here. So actually we don't have to change anything here, except that if we, actually I should say this in the beginning. So we could simplify the derivation a little bit by assuming mu equals to 0. The reason is because that when we define this as n squared, we are subtracting that x n bar anyway. So recall this is defining as 1 over n xi minus xm bar squared. So what this suggests is that if I change my mu by shifting my random variables, this Sn squared will not be affected. So that's why without loss of generality, we can assume this to be 0, and that can simplify the derivation. But it doesn't matter that much. So what we did here is correct. Okay, so with this, then what's left here is basically we are going to left multiply this to that, and then right multiply this. Okay, so finally, we would actually be able to have just, so let me just say, without loss of generality, just assume mu is 0. Okay, so now you will see this becomes G dot mu squared plus sigma squared can be simplified as 0, 1. And that will make our calculation of this part easier. So you see, when it's 0, 1, 0, 1 here, 0, 1 transpose here, what we will obtain is only retain this dot, this one, the variance of xi squared, and we're done. Okay, so basically, we would have just as so root n by the delta method, finally, as n squared, which is the g function applied to this mx minus sigma squared, which is the g function applied to the mean, will converge in law to standard
to normal distribution, 0 mean, and finally, we will have just the variance of xi squared. That's it. So you see, we can still derive the asymptotic distribution of the sample variance using the delta method, and it is still a normal distribution, and the asymptotic variance simply depends on the variance of xi squared. And when the xi is normal, we can further simplify it. Okay, so when the xi is normal with variance sigma squared, then what we know is that then this variance xi squared can be simplified just as 2 times sigma fourth. So that's why we said normal distribution is super special, because it's only defined, it's purely defined by 2 parameters, the mean and the variance. And other further moments can be written based on mean and the variance. And as you can see from here, or actually, I think, no, 0. Yeah, this that only holds when the mean is 0, because we don't need to care about that center anymore. Okay, so with this, then you see, we can derive the asymptotic distribution of the sample variance. And you can see, interestingly, even though by definition, the sample variance must be non-negative, right? And we know that a normal distribution has the support on the whole real line. How is that possible, right? There seems to be some discrepancy, because this one clearly cannot go to negative infinity. The reason why we have this and it still holds asymptotically is because this normal distribution is very concentrated around its mean. So in other words, this Sn squared will be very concentrated on the sigma squared. So even though this support can go to the negative part, but the density over there is very, very low. So that's why it's a very good approximation. Okay. So if this is something, again, I want to encourage everyone to play with this using numerical simulation, and you will see how magically it works. Yeah, you will just have a normal distribution when your sample size goes large. Okay, I think I will stop here for today, right? We have covered a lot of things. So next time we are going to talk about another finer approximation than the delta method. So what happens when we go to the second derivative, not just the first? And also we are going to further extend this, right? Right now we talk about the asymptotic distribution for the mean, sample mean, the average of the squares, and the sample variance. How about the sample correlation coefficient? A very important statistic we use in daily lives. So what's the asymptotic distribution for that, for the correlation coefficient? So we'll see that next time.